Okay, so welcome to our fifth and final optional examples class of this session on definitions, proofs and examples. So let's have a look. What have we got on today? Well, I thought we'd start with something that could be done using proof by contradiction. Don't have to do proof by contradiction on this one, but it's about time we had a proof by contradiction. So I'm going to suggest we do this one by contradiction. So remember our notion of absorption for sequences, and just want you to write down a quick and easy proof using the definition of absorption that if you've got a pair of disjoint sets in R, so their intersection is empty, and you take some sequence of real numbers, just proves that they can't both absorb the same sequence. And that should be quick deduction from the definitions, but of course you have to know the definitions to be able to prove it. It doesn't count as a proof to say they couldn't possibly both absorb it unless you can say because. So I'm going to suggest proof by contradiction, though it doesn't have to be done that way. Once you have done this one, you might want to figure out what might be a better result, a slightly more powerful result that this would follow from, that really tells you what's going on relating to intersections and absorption. But for now, let's start by proving this one by contradiction, and I'll give you a bit of time to work on that, and I'll look for my pause button. Okay, I'll give you my version of this. I don't know whether anybody's got it yet, but if you've got it, well done. Let's give you a quick proof of this. So here's how we'll go. We'll start with suppose for contradiction. This is one way of saying it. This is our assumption, which we're going to show leads to something ridiculous. If we end up with something ridiculous, having made this assumption, we'll know that this supposition was wrong. So we'll suppose for contradiction that A and B both absorb xn. And we're given the conditions above. So remember, throughout this, you should remember that A and B don't overlap. A intersection B is empty. So, of course, what I'm going to do is I'm going to show that actually some, in fact, infinitely many of the terms of the sequence will actually turn out to be in both A and B at the same time, which will make the intersection non-empty, which will be ridiculous and give the contradiction. So how do we do it? Well, since A absorbs xn, there's an n1. I'm going to need different, at first at least, I'm going to need different integers, different stages for each set. So there's an n1 that works for A, that's a natural number. So n greater or equal to n1 implies xn is in A. And there's an n2 so that n greater or equal to n2 implies xn is in B. That's similarly, I should have said, since B absorbs the sequence. What have I done so far? All I've done is use the definition of absorption, and I had to be a bit careful because each set gets its own number. Different sets will have their own different capital N's. That's why I've used a capital N1 for A and a capital N2 for B, because at first we don't know the same one works for each. But we can find one that works for both of them at the same time. Any suggestions? What could I do here to find... Yeah? Yeah. Let's take N3 to be the maximum of N1 and N2. And of course that's still a natural number. then n greater or equal to n3 implies xn is in A and xn is in B. Or in other words, xn is in A intersection B, which is empty. A intersection B is empty, so this is clearly ridiculous. So this is impossible. This contradiction proves the result. Okay, we supposed that the sets both absorbed, the two sets both absorbed the sequence. We got a contradiction because the intersection was empty and that was impossible. But what have we really done? What would be a better way of saying all this? What does that argument really show? Any comments? Because we've actually managed to do, if you follow through that argument, you've actually managed to show something a bit better. Essentially the same argument, I would say. So not in the same setting, but whenever two sets absorb the same sequence, so what have we really done? Suppose you've got two sets, A and B, and they both absorb the same sequence. What could you deduce? Based on the argument you just did. Yes? You certainly could prove that the intersection is not empty, and that would solve the problem we had, but actually you've proved a bit more. What else could you say? What did we actually show? We showed that all terms beyond n3 were in the intersection. And what does that say? All of the xn for n greater than n3 were in the intersection, A intersection B. So that says more than just that A intersection B is not empty, yes? No, we can't prove that it's sequentially compact, I don't think. No. But we managed to show that all terms from a certain point on lie in A intersection B. And what's another way of saying that? Well, okay, I'll give it you. But from some point on, all terms are in A intersection B. That means that A intersection B absorbs the sequence too. So what you've shown is that if A absorbs the sequence and B absorbs the same sequence, then the intersection, A intersection B, also absorbs the sequence. Notice that's different from saying A absorbs xn and B absorbs xn. A intersection B is another set. Let me just rewrite that. It's another set, A intersection B. But we showed that if you go far enough, you're in A. If you go far enough, you get stuck in B. So if you go past those 2 points, you're going to be stuck in both sets simultaneously, which means you'll be stuck in A intersection B. And that's what our argument really showed. And then you can go back, if you prove this result, the other one follows immediately. As you said, if you get stuck, if your sequence is getting stuck in A intersection B, then in particular A intersection B must be non-empty. Okay, so that's enough on that one. Right, now let's move on. Here's one we didn't have time to get to last time, so let's have another go at it. The idea of this question is hopefully to make sure that you're not confused about the sequence criterion for closedness. This question involves the most common mistake when I've asked people to write down the definition of sequence criterion for closedness. When I've asked people to write down in the past the sequence criterion for closedness, the most common mistake is that people write down something like this. So, since what this means is that the set has exactly one element, it's rather different from a criterion for closedness. Though it does, of course, if it's got exactly one element, then it is closed, but it's probably not what people want to mean. So, when I've asked people to write down sequence criterion for closedness, I quite often get people writing every sequence in E converges to a point B. And sometimes people write things like every sequence in E converges in R, and nobody writes the set has exactly one element. But these three are equivalent. So here's your task to try and decide which ones easily imply the other ones so that you can get all three of these equivalent. You should easily see that C implies the other two very easily. So if you've got exactly one element in the set, there aren't very many sequences available. So it's very easy to show that they all converge in R, and it's very easy to show they all converge to a point of E. B implies A is very easy as well. So some of these things come for free. C implies the other two easily. B implies A is easy. So what you're really left with is A implies C, or not C implies not A. So I'll leave it to you to think about the most efficient way of proving these three are equivalent. And I'll come round and see how you're getting on with it. Okay, I'll now give you my version, but I already heard somebody coming up with the right idea, so I know that some of you got it. So, first of all, I'll do C implies B. So, the structure, I'll do C implies B implies A, and then I'll do, and A implies C, except that last one I'll do as not C implies not A. And then we're finished, because I've just asked about this. How does that show they're all equivalent? Well, you can then deduce, by going around the cycle, you can deduce any of the statements from any of the other ones. So say you know that B is true, then you'll be able to deduce, let's get an arrow up. So if I manage to prove all these, then from B you can deduce A, and then you can deduce C from that afterwards. And so you'll have also got B implies C going via A. And then suppose you know A is true, then from A you can deduce C, and then C will then tell you that B is true, and so you can deduce them all cyclically. So this is an efficient proof structure if we can do it. But sometimes it turns out to be hard to prove the implications this way, and sometimes you really do have to prove two separate if and only ifs because it's just too hard to do it. In this occasion, it turns out to work out nicely, and this is quite an efficient way of doing it. So let's get rid of that arrow. And so C implies B. If E's got exactly 1 point, so given E has exactly 1 point, say E is the single, we're in R, so not a vector, it's just A. Same thing works in any dimension, of course. I'm just doing this in R, but you can do it in higher dimensions, it's fine. So now what happens? Well, there's only one sequence available in E. The only sequence in E is the constant sequence whose all of whose terms is A. There's only 1 point. And of course, that converges to A. Which is an element of E. So B holds. Every sequence in E converges to a point of E. Essentially trivial, right? I would have been entitled to say C implies B is essentially trivial. But I've just written it out for you so that you can see how it will go. B implies A is trivial. Because any sequence that converges to a point of E converges in R. I mean, the converging in R is a weaker statement than saying it converges and converges to a point of E. So that one's trivial. So that gives you B implies A. So all we need is the last one. If I say I'm going to not C implies not A, that means if E's got at least 1 point, at least 2 points, then there's some bad sequence in it. So now I'm going to do not C implies not A. So given C fails, just to remind you, E was assumed non-empty, and now we're told that E doesn't have exactly 1 point either, so E has at least 2 points. So let A and B be in E, with A not equal to B. Of course, one could always write this down anyway, but it's only valid right now because we know E's got at least 2 points. And then I heard a statement from someone saying what you could do next. What can you now do? You've got 2 different points in E. How can you make a bad sequence out of it? Yeah? Division by 0. A over B. Okay. But we need to find a sequence in E which doesn't converge. So we can't. If we start dividing by things, we might end up not in E anymore. Any suggestions? How can I use these 2 different points? E might only have 2 points, so we've got to make do with these 2. There's got to be enough. Yeah? Alternate between them. You can write down a formula for it if you like, but that's good enough for me. Clearly this is a sequence in E which doesn't converge. So since A not equal to B, this sequence in E clearly does not converge in R. So A fails. And we've done it. That's it. Yes? Okay. 0 points is eliminated because we're given in the question that E is a non-empty set. Okay? So that was given. I agree that you should worry about that. But fortunately the question says that E is non-empty. So we're given that E is non-empty, and we're given that E doesn't have exactly 1 point. So we know that E's got at least 2 points. I'm not saying that it's only got these 2 points, but as soon as you've got 2 different points in E, you can do this trick. So there may be a whole load of other points in E, but it doesn't matter. Because as soon as you've got 2, you can perform this trick and get this sequence alternating between 2 points of your choice in E. Does that make sense? Yeah, okay, good. Okay, we've done that one. Right, question 3 is about finding examples, just writing them down with with brief justification, it says. Okay, you're allowed to use the Heine-Borel theorem. So you're allowed to quote the Heine-Borel theorem, which hopefully you remember. A sequentially compact subset. Well, your sequentially compact has got a definition. Not worry about the definition, okay, because we know sequentially compact is equivalent to being closed and bounded. Okay? And that's what we're going to use. So, A is you want a closed set which is not sequentially compact. B is a bounded set which is not sequentially compact. C, sequentially compact set that's also open. And D, well, that's something else. A sequence which has no convergent subsequences. And that will do for question 3. Okay? So, what I'll do, I'll pause there and see if people can think up some examples of those. Okay, let's get some examples down. Let me first remind you again, for E, a subset of R, E is sequentially compact if and only if E is closed and bounded, both closed and bounded. So, if you fail either, you fail to be sequentially compact. So now when we look at A, you're asked for a closed set which is not sequentially compact, then it better not be bounded, because otherwise it will be. So we need a set which is closed but not bounded. So by Heine-Borel, we need a set E. Oh, is it F? It's F, gosh. Closed but not bounded. And I've seen various examples around, but you can just get away with using the whole real line. That's a standard unbounded and closed set. So that does that one. What about the next one? This time, we want a bounded set which is not sequentially compact. So what have we got to avoid? It's bounded and it's not, we don't want it to be sequentially compact, so what mustn't it be? Well, if it's closed and bounded, we've had it, so it mustn't be closed. So, who's got a favourite example of a bounded set which isn't closed? in the real life? Anybody want to tell me one? I'm happy to give you one, but if you happen to have one, then you can tell me one. Nobody wants to tell me one? Yes? The rational numbers is not closed, but unfortunately the rational numbers is also not bounded. So we can't use all of the rational numbers. You could use some subset of them, but we can't get away with using the whole of the rational numbers. So, okay. Who's got a bounded set? Who's got a set that is bounded but isn't closed? Yes? So, okay, the open interval between 0 and 1, though actually the nth stuff isn't relevant to whether it's closed or not. That's the nth stuff is relevant to whether it's not open. Okay, but there are arguments you could do along those lines. But yes, okay, so so f could be the open interval 0, 1, and this is clearly bounded. And by now I'll say, and it's standard that it's not closed. We know all about intervals. We know all about bounded intervals. We know which ones are closed. We know which ones are open. We can say, just look at it and say, this is a standard bounded interval in the real line, and we know this one's not one of the closed ones. Okay? So that does that. Okay, there's not many choices this time. E has to be closed and bounded and open. Now, that means in particular that it's clopen, and there aren't very many clopen sets. So there are only 2 clopen sets, and only one of the clopen sets is bounded. So what's the only possibility? The empty set, that's right. So there are only 2 clopen sets. And R is unbounded. So E equals the empty set is the only possibility here. Is it E or F? I've gone wrong again. Oh, it's E this time. We must take E to be the empty set. Which is fine. The empty set, standard, that it's open, and it's closed, and it's bounded, and it's sequentially compact. Actually, if you go back to the original definition of sequentially compact, it's a bit odd. It reads, every sequence in the empty set has a convergent subsequence which converges to a point of the empty set. Which does sound a bit strange, but it is actually true, because there aren't any sequences to violate it. Because there are no sequences at all in the empty set, the statement, every sequence in the empty set something happens, is so-called vacuously true. But if you prefer to note that it's closed and bounded, that's okay. D, sequence with no convergent subsequences, plenty of these around. Anybody got a favourite? Who's got a sequence which has no convergent subsequences at all? Any suggestions? We saw last time that this happens if and only if the modulus tends to infinity. So all you have to do is take any sequence where the modulus of the terms tends to infinity and you're done. So you've got unbelievable amount of choice. the easiest one is to take x equals n, but there's plenty of others. Then every subsequence of xn also tends to infinity and so doesn't converge. So no convergent subsequences. Remember, tending to infinity is a particular kind of divergence. It's one of the special kinds of divergence available. So it certainly stops it converging. Okay, and that does that one. Well, I guess we're out of time. So we'll stop there and we'll resume with the lecture at 3 o'clock. I think there's going to be an announcement relating to the election as well. So